Hi everyone, and thanks for tuning in. My name is Demas. Today, I'd like to present to you my final project for Mechanical Engineering 400, Computer-Aided Design, under Professor Marshall Long. I set out to design a kinetic sculpture, like the one seen here in the Corning Museum of Glass in upstate New York. I've always been mesmerized by these machines, and thought to myself, wouldn't it be cool to have one that could be 3D printed using a MakerBot Thing-O-Matic 3D printer? This open source platform uses fused deposition modeling to lay down successive layers of ABS, a common thermoplastic used in everything from cell phone cases to Legos. The device builds up the desired part cross-section by cross-section, shown here in high speed. While increased size increases the print time significantly, increased complexity, particularly in voids and holes, does not, and instead allows for less material to be expended, as 3D printing is an additive process as opposed to a subtractive manufacturing process that could employ the use of a CNC mill or lathe. Through careful design and planning, I brought the idea to reality over the course of a few weeks using the computer-aided design and manufacturing tools at my disposal. Starting first with concept sketches, I progressed to computer simulations using SolidWorks, a 3D modeling and analysis software package which I used to perform both motion analysis studies and finite element models to confirm my designs. I finally built a full working prototype with the Thing-O-Matic 3D printer detailed earlier. I'll quickly go through some of the more interesting parts of the development of the machine, show some time-lapse photos of the 3D printing process, and then get to a demonstration of the device at the end. One of the most useful tools in the development of this device was the motion analysis studies provided by SolidWorks. This study shows a flaw with my initial design, in which the ball would never escape from the helical lift. Another motion study here shows an early design in which the ball would jump off a ramp and land on a platform. With the use of the motion study tool and appropriate input parameters such as friction, it was clear that this design would fail. Another useful tool was the finite element analysis studies, which I used to analyze the stresses on the handle during development. Here, the outcome of a vertical force on the handle is shown, and here, the outcome of a torque on the handle is shown. These studies confirm that in combination, the use of ABS and the geometry I specified would give a rigid design for the handle that would not yield during operation or moderate unnatural loading. After the design was finished, it was time to print. This sequence of images illustrates the helical lift being 3D printed. After a print time of approximately 2 hours and 15 minutes, the support material needed to be removed. The part then emerged. Now, onto the base and track. Here, you can see the final result from the printing process, including the support material. This print, along with the handle that is not shown, took over 16 hours to complete. Now, the final product. Here is the device fully assembled. Let's make it move. Seen at the bottom, this feeder track aligns the ball bearings for insertion into the lift. Gravity pulls the ball bearings into the cutout, and a few turns of the hand crank brings the ball to the top. To solve the problem found at the top of the lift, a small arm was attached to the helix. As the user rotates the handle, the small arm sweeps around and gently pushes the ball away. The ball rolls down and falls back into the feeder track to be brought back to the top again. Let's look at it once in simulation. Great, and let's check how the prototype works. Success! All of the hard work in simulating and running analysis has paid off.